Around with this for a while, and this is something that the average person can do. It's very easy to overall just create a neural network and then create a lot of dimensions for the vectors, which is what hyperdimensions, hyperparameters, and hypervectors are overall, right? Is they're just with a hypervector, you're just creating a large number of dimensions as opposed to a typical vector. Typical vector, the number of dimensions depends on the vectorization method, but let's say you're like 100 dimensions would be common. Whereas with hypervectors, as with the example that we're experimenting with here, we're dealing with like 10,000 dimensions. So 100 compared to 10,000, that's quite a few magnitudes of difference. But generally speaking, overall, like that's the major difference between a vector and a hypervector is just that huge amount of dimensionality, and that huge amount of dimensionality and that complexity builds a model in and of itself, right? It ties into complexity theory, and that's kind of why and how HDC works overall. Is it works because complexity theory works, and then so within that, though, a part of kind of that known complexity is that you can't train parameters. You can't train these parameters or set the parameters of the hypervectors, right? That's kind of one thing that comes out of this. So within the hypervectors, part of this complexity theory is that if I take a completely random vector, like one of these vectors, there exists another hypervector, another vector that exists that is completely orthogonal to that vector, like the complete opposite of it. And then I can utilize that and that knowledge to essentially measure distances between hypervectors, and that measuring of distance between hypervectors is how essentially we utilize HDC as a process overall. But so that process is very distinct from neural networks and from deep learning overall. And then so there's been a huge distinction between the two, right? They're seen as two like completely separate models. But from my research and what I want to showcase and highlight within this is that like there's less separation between the two concepts that people think. I think that overall, I mean, all of these concepts are related. But so I think that my goal within this is to prove to you that I can take a HDC model, hyperparameters and hypervectors, and I can train those hyperparameters and those weights into an effective model that will get us effective accuracy. So essentially, I can take the problem with HDC is that you can get like a very good and accurate measurement, but you can't necessarily improve upon it, right? So, and then with a neural network, that's the exact opposite. You get a very low score generally up front, and then you can train and improve on the accuracy of that score. And then so I just want to combine the best of both worlds, right? I want a model that relies on hyperparameters and that I can train those hyperparameters. And then so that's essentially what I do with this model. And then how I've been able to do it is very straightforward. I create this projection matrix, right? And then so all of it comes down to this projection matrix, really. So essentially, my neural network that I create, it's created based off of 10,000 dimensions, and then the 10,000 dimensions are my 10,000 hypervectors, or also 10,000 hyperparameters. And then for the hyperparameters, it's 10,000 dimensions times 10 classes, and then so it's 10,000 times 10. To get the number of hyperparameters that are in the model fully that it'll be training within that, right? And then essentially going down, again, highlighting the major thing that like how this model works overall, how these parameters train is this projection matrix. And then so just very simplistically, what it does is, let's take a concept of cat, a cat and dog, right? And then those concepts get projected into a matrix, and so into like a 3D graph, right? And then so the concept of cat gets plotted, and then so there'd be like different plot points all on the graph, and that would generate a shape, a three-dimensional shape of this concept of cat in this instance. And then we take that shape and then we feed that through the network. And then how we do that is, again, so it starts off as a three-dimensional shape. So the very first step that we need to do is we need to flatten the shape. So we flatten it into completely like one-dimensional flat. And then from there, we take it and then we blow it back up. So we take the flat image and then we make it big again. But if you like know anything about like doing this with like maps and globes and things like that, by doing that, you don't get the same image, right? By taking a globe and then flattening it, and then reprojecting it, you don't just like, it doesn't reproject back into a proper globe. There's distortions within that, but that's what we want. We want those distortions. So essentially what we've done is we've taken our original image, so shape 1, our flattened image, shape 2, our blown up image, shape 3, and then between these three shapes, we can essentially measure the distance between these three shapes. We inject some non-linearity into there, so some like probability and some predictability, and then that's essentially what our model is training off of and guessing off of is essentially these these three different shapes is really how it works, right? And then these three different shapes get projected onto this matrix, and then this matrix gets updated, and that's like the weights of the matrix get updated, and that's how the model its weights get adjusted as it learns. And then so from there, it's a typical training loop, right? So everything here is very straightforward. I have it's a loss rate. So I have loss. I'm measuring the loss via gradient descent. I have my standard optimizer. In this instance, I'm utilizing Atom optimizer, and so I have my loss rate that we measure. I train it for a number of epochs. Loss rate starts off very high, right? At 17, and then it goes down to 5. But which would be high overall, but test accuracy ends up at 73.63%, which is not anything to write home about. But this is, I mean, that proves the validity of this model, that you can do this, right? Like I was like, if you do like a lot of models where you try to do this, you'll get into the teens. And then so being able to do this and get 73% accuracy proves the concept to me. And then so the next thing I wanted to do within this is take it a step further, right? Like how exactly would I take this to the limit? And then so essentially I would increase the number of epochs, decrease the learning rate, and then I would rather than making that the learnable projection matrix, I would just use a fixed projection matrix, and then I want the hypervectors to stay learnable, but the projection to stay fixed. And then that's kind of, these are the major changes that I make within this. Other than that, it's all very straightforward and exactly as it was, but I'm increasing the number of training epochs within this, so it takes a lot longer to train. But within this, you can see with these modifications, the loss starts off a lot lower, 2.2, right? So the loss on this starts off lower than this one ever even got to. And then with just 3 epochs of training, I get up to 65% accuracy. And it's going up pretty quickly, right? So my expectation is that by the end of training, this model would score within the 80s, perhaps up to 90%. After those 50 epochs is kind of what my thoughts are within this. I stopped it after 3 epochs just because it was taking so long to run and to train. It take a few hours to fully train it out, but this model will, I wanted to just prove out that this model would outperform my base model, so it would outperform the 73% accuracy, which I can prove out that it will at this point. Again, I think the end result, you'll get between 80 and 90% accuracy with this model. So it proves the concept overall that you can, in fact, train hyperdimensional HDC network as a neural network. And then so going back to the top of the video, right? It's often thought that these are two very separate processes, that what HDC does and what a neural network does and what deep learning do, that they're very different, right? And that you can't associate or join them, which is why you typically when you try to do this process, you get bad performance out of the neural network. But just by essentially implementing this projection matrix within that, and then training everything based off of this projection matrix, it solves that problem. And then it essentially acts as the bridge between these two concepts. And then to me, more and more, what we're finding out about these things is that they're correlated and they're related. To me, I believe more and more that algebra and linear algebra is directly correlated to geometry and calculus and the probabilistic aspects of that. And then same thing, I think that relativistic physics is an extension of and corollary to quantum mechanics and quantum physics, and that everything is just this generally related cycle, right? And I get to this when you play around with HDC models and how they work. Essentially, the shape that they produce, what they're doing, the complexity of the model, how it's able to operate, is it operates like a manifold, is the shape that it produces. And then it just essentially runs this data set through a manifold. And the manifold shape is essentially like a brain with different folds, right? It's just running this information backwards and forwards through folds. And if you studying brains, everything else, I think that that's the essence of everything, right? It's just essentially crunching data and taking noisy data and turning it into signal data. I think that is the essence. I keep refining this, but I think that's the essence of compute. At the end of the day, when I come to this, is that what compute does and what computation does is you're essentially sifting through noise and trying to convert noise into signal data, into meaningful data. And then that's what computation does. Are you successful at that? Can you successfully take what is currently classified as noise according to the system or any system, and then turn that into a meaningful signal, something that actually has meaning behind it? And if you can, that's positive computation, and that's a computational system overall. And then so I think that these are all just computational systems: HDC, neural networks, my brain, your brain, an LLM model, etc. They're all like animals. They're all just extensions of essentially these manifolds passing and going forward and with data and processing data in different ways. And then so if you like this type of content, please like and subscribe. Thank you very much.